Welcome everybody. We are taking a look at the solutions to problem set number 4. Exercise 1 was pretty easy, just to get comfortable with the notion of an operation on a set and checking the group axioms. We start with the natural numbers. So one, 2, 3, 4, and so on. 0 is not included in my natural numbers. If I want 0 to be included, I would write n sub 0. And the operation on this set, a circ b, is a simple addition. Now, are the natural numbers closed under this operation? Of course, the sum of two natural numbers is a natural number again. Is this associative? Of course, we learned that in kindergarten, that adding natural numbers is associative. We are not touching upon the axiomatic construction of the natural numbers here. We simply take them as given and take as given that the rules we learned in high school or school are valid. So this looks good, but we have no identity because 0 is not included. If we would include 0, things would look good so far, then the group axioms would be satisfied, but we have no inverses. We can't have because we have no identity. Even if we had 3 plus something equal to 0 would lead to a negative number, which is not in the natural numbers. So the natural numbers are not a group under addition. There are notions for that like magma and monoid, but we are not going to need them, so I won't even introduce them to you. Okay, next are the integers. With the operation of taking the difference of two integers, then of course the integers are closed. The difference of two integers is an integer again. Now, associativity. Let's try it. A composed with B composed with C is by definition A minus B minus C. Whereas A composed with B composed with C would be first B minus C, and then, because of this here, minus, which is A minus B plus C. So we see, nope, they are not the same. So this isn't even an associative operation. The set is closed, but this is an easy example of a non-associative operation. Would we have an identity? Well, no. This is also interesting because 0 composed with B would be minus B, but B composed with 0 would be B. So 0 would be a right identity, but not a left identity, because it changes B if B is not 0. So again, a simple example for an operation where there is no identity, at least from both sides. Are there inverses? Well, if we don't have an identity, we can't have really inverses, but let's say at least this is a right identity. So do we have a right inverse? Yes. A composed with A would be A minus A, which would give me this right identity, but I can't really have inverses if there's no identity from both sides. But if there were an identity, then every element would be a self-inverse element. Now we take the rational numbers, so all fractions without minus 1, with this strange operation. A circ B is A plus B plus AB. First of all, we have to convince ourselves that G is closed under this operation. Well, the only possibility to fall out of this set here is if this gives you -1, because it will stay rational. If I add rational numbers and if I multiply them, I will again get a rational number. So of course, this here is a rational number. The question is, can it be -1? Okay, let's assume this here would give -1. Then I take those two, take out the a, and there remains 1 plus b. I bring this b to the right-hand side with -b. Draw out the -1. So I end up with this. Now by assumption b is not equal to -1, so I can divide by that. So here and here, let's forget that. And I would end up with a equals -1, which is a contradiction because a also is from this set. So indeed, this set is closed under this operation. But there was some work to do. Is this associative? The answer is, so first of all here we have yes, because a cannot be -1. This is indeed closed. Is it associative? The answer is yes. If you don't believe it, well, spell it out for yourself. I'll show it to you and I'll be lazy and will not do it on the blackboard. It's simply writing down a lot of stuff and not get confused with the parentheses, and then you'll find out it is indeed associative. In the solution I have written this little star instead of the circle here, but for obvious reasons I don't want to write that little star here. Is there an identity? Yes, there is. It is actually the 0, because a circ 0 is a plus 0 plus 0 is a. And we also have to check for identity from the left. This is 0 plus a plus 0 is a. So 0 is the identity. And actually there are inverses. We are looking for a b to a given a such that a composed with b is the neutral element or the identity. So 0. So let's try that. We have a plus b plus ab is equal to 0, and we try to solve for b. So I take these here, and they are equivalent to b times 1 plus a in parentheses. Bring the a to the right-hand side, and now because a is not -1, I can divide by 1 plus a, so minus a divided by 1 plus a is indeed the inverse element. And obviously this is commutative, because if you interchange a and b, you get the same expression here. So this was actually not necessary because we have a commutative relation. So putting everything together, the rational numbers without -1 with this strange operation here is indeed a group, actually a commutative group with infinitely many elements. So, and of course, a simpler example of an infinite group would simply be the integers, but not with minus, but with plus, with addition as composition. So here are two different examples of an infinite group. Okay, next example. We take one of the known fields, the rationals, the real numbers, or if you know them already, the complex numbers. And as operation, we simply take addition. And then by the known rules you've learned in school about the rationals or the real numbers, of course, the sum of two of those is again an element of this so-called field here. Addition is associative. There is an identity, which is of course 0. So often if we write plus, if we have additive notation, we do not write this as e or sometimes 1, but as 0, even in abstract additive groups. And the inverse we do not write as a inverse, but simply as minus a, because here obviously minus a is the inverse of a, because a plus minus a is 0. So these are examples of infinite groups, and they of course are commutative because addition is commutative in the rationals or real numbers. And again, quick, oh, this is of course not always a, I'm sorry, I forgot that all the time. So this is e now. If we take the numbers from before and exclude 0, then under simple multiplication this again becomes a commutative group, because obviously the product of two such elements stays in there. Remember, the product of two numbers that are not 0 cannot be 0. Multiplication is associative. There is an identity, namely the 1 in this field, and there are inverses. A inverse is now written as 1 over a, and this is always possible because we excluded the 0. The star here means k without the 0. So these are another examples for infinite commutative groups with infinitely many elements. All right, next exercise. This is an easy way to construct new groups from already known groups. If I have a group G with composition or operation circle, which I call circ for short, and here H and dot as operation, then their direct product as a set is given by the Cartesian product. So you simply take these tuples here, A belonging to G, X belonging to H, and G cross H or G times H is just the set of all those tuples. And as operation, you take one tuple star the other by simply taking component-wise. Here in the first component, the operation in G, and in the second component, the operation in H. And we are to verify that this is actually a group. So is this new set closed under this operation? Yes. Why? Because this is obviously an element of G, because G is closed. And this is an element of H, so again, this here belongs to G times H. That's it. Associativity, here it's really okay to be lazy, because in each component the operation is associative. So of course it is associative on these tuples. It's just a nuisance to write that down, so here it's really okay. Because of component-wise associativity, we get associativity of star. I think this is enough. If not, spell it out. Even if you're a beginner, it might be a good idea to actually write that down for once, and then you will see, well, it's in every component only associativity. So then, is there an identity? Of course. The identity of our direct product is simply this tuple consisting of the identities of G and H. And now if you compose any element with that, then component-wise you compose with the identity of the corresponding group. So here you get A and here you get X if you combine AX with this. So again, you get AX and also from the other side. So this here is clear. If you're a student that is beginning his studies and this is an exercise that you have had to hand in, please spell out the details. Don't be lazy there, because then you might not get full credit. You write that down and then you spell out what I just said, but I'm not going to do that here. Are there inverses? Yes, there are. Because what might be the inverse of this tuple? Well, of course, you simply take the inverses in each group, in G and in H, and then this combined with this element gives you the identity. Again, spell out the details if this is one of your first exercise sheets that you hand in. So we have verified that indeed this direct product with this operation here is a group. Or actually this combined with this operation is called the direct product and it is a group. Now in part B, we are concerned with commutativity. We have to show that the direct product is abelian if and only if both G and H are abelian. The if with a double F means these are equivalent. So if this is true, then this follows, and also the other way around. If this is true, then this follows. Most of the times it is better to do it both ways, so show one implication and then the other. Here I think it might be more efficient to do it in one way. So we start here. G cross H or G times H is abelian means, it means that here I can switch orders. So for all A, B, and G, X, Y, and H, or for all AX in G times H and BY in G times H, which is the same, this is true. Now I simply apply the definition on both sides. I'm not going to write that down all the time. So this here is simply the definition of the operation star. We do the operation component-wise. So here we have A circ B and X dot Y, and here we have B circ A and Y dot X. And now we use the definition of equality in such a direct product or Cartesian product. Well, when are two tuples the same? Of course, when both of their components are the same. So always for all A, B, and G, X, Y, and H, we have that these components here must be the same. So A circ B must be the same as B circ A for all A, B, and G, and X dot Y must be the same as Y dot X for all X, Y, and H. And this exactly means that G is abelian and H is abelian. And because we only did here equivalences, this shows that those statements are equivalent. If this was too much, then maybe try proving both implications separately. For example, start with that, then it's very easy to see that this is true. If this is true, you may consider these elements A and here the identity in the same B and the identity and multiply those with star. And then you know you can interchange that. This will lead you to AB equals BA. But then you also have to use this definition of equality here. So I think this should be easy enough to understand. Now last question, what happens with the direct product if the groups are simply the real numbers and both operations circ and dot are addition? Then this is simply the well-known plane R to the 2 with vector addition, except that we write the vectors as AB instead of AB, but this is the only difference. This is actually the well-known vector space you know from school, from two-dimensional geometry. So just that you have a very concrete example of such a direct product.